metallic character as well as non-metallic character are called metalloids. And again, we have got the same type where some people classify the elements and they calculate the percentage of the non-metals present and the percentage of the metals present. And if you go on studying the properties of all the elements in the periodic table, almost 75% of the elements printed in the periodic table are metals. Hardly 25% are non-metals. That means we have got majority of the elements exhibiting the metallic character and very few exhibiting non-metallic character. Our focus in today's presentation is only to study about the metals and not about the non-metals. And amongst the metals, we have got these categories. We have got the blocks. If somebody has to study the periodic table in the simplest manner, then we have got a small patchwork of elements starting from lithium up to radium, whose electronic configuration, whose general electronic configuration is NS1 to 2. That means the added electron enters into the subshell, where, as you know, N is called the principal quantum number. This is on the left hand side. On the right hand side, we have got NS1 to 2, NP1 to 6. This is another small patch, relatively bigger patchwork as compared to S block elements. In between S and P block elements, we have got a special class of metals or special class of elements called the transition elements or D block elements, and these elements have got the general electronic configuration of N-1 D 1 to 10 NS 1 to 2. That means the outer electronic configuration remains practically constant. As the atomic number increases from scandium to zinc, then yttrium to cadmium, then lanthanum to mercury, right? The added electron enters into the inner D subshell and not the outer S subshell, right? And we have got two sets of 14 elements each, which are kept almost at the bottom of the periodic table with the general electronic configuration of N minus 2 F 1 to 14, N minus 1 D, maybe 0 to 1 NS2. Again, as usual, N stands for the principal quantum number. In the previous case, the added electron, as the atomic number increased, the added electron was entering into the inner D subshell, and in these elements, which are kept at the bottom of the periodic table, as the atomic number increases from cerium to lutetium, from thorium to lawrencium, the added electron is little more buried, is entering into the innermost F subshell, keeping the outer D subshell and S subshell practically constant. These should have been placed actually in the third group of the periodic table. But as I said earlier, to bring about the compactness and to make the printing, carrying, displaying of the periodic table so simple, so easy, these two sets of elements have been separately kept at the bottom of the periodic table. And therefore, these are called the inner transition elements or sub-transition elements, or otherwise more popularly known as F block elements. For the high school students also, this entire periodic table can be remembered by simple analogy that I am giving now. The entire periodic table can be compared to two slices of bread. Thin slice is S block. Relatively, a bigger slice of bread is P block. And in between, we have got the colored jam applied. In between the thin slice of bread and relatively bigger slice of bread, colored jam is applied. that colored jam is supposed to be now D-block. And if excess of jam has been applied, and when you press the thin slice and a relatively bigger slice of bread, some excess jam will fall down. What has fallen down should be F-block elements or inner transition elements. Why I am giving this comparison is because if the bread is properly baked, it is almost colorless. S-block elements are colorless. P-block elements are colorless like a slice of bread. The colored jam applied represents the D-block elements, and what has fallen down must have been diluted, and that diluted jam is comparison for the F-block elements or inner or sub-transition elements. So periodic table means 2 slices of bread, in between colored jam is applied. When you press the 2 slices of bread, some excess jam will fall down. That should be referred to as the D-block elements. This, I think, is the simplest way of remembering periodic table. Now, again, to make the study of periodic table much more simpler, great people have classified the elements like the groups and periods. What are these groups and periods? In fact, each vertical column is called a group, and each horizontal row is called a period. And if we have got groups and periods, how many groups are there? Totally, there are 18 groups in the entire periodic table. And how many periods are there? We have got 1, 2, 3, 4 like that, 7 periods, right? Amongst all these periods and groups, first period is shortest because it contains only 2 elements. One is hydrogen on the left hand side and another is helium on the right hand side. Elements are classified into 4 blocks that we already studied, and in fact the 6th period is longest and 7th period is incomplete because the elements which may be discovered in future may be accommodated in the 7th period. And in fact, in the 2nd, 3rd, we have got 8 elements each. First period, we have got only 2. 2nd and 3rd, we have got 8. And we have got from 4th onwards, 18 elements. And this is how there is a different way of classifying the elements into groups and periods, into blocks such as S, P, D, and F, depending upon the number of electrons present in the D subshell, or F subshell, or S subshell, or P subshell. Now, coming to the main topic of today's presentation. My presentation, as you know, is mainly on the D block elements. What are these D block elements? The very simple and complete definition of the D block elements is elements which have partially filled d orbitals, either in their atoms or in their most commonly occurring oxidation states, are called D block elements. The second part of this definition is more important. I have seen in many textbooks, the definition printed is elements which have partially filled d orbitals are called the D block elements. But strictly speaking, it is incomplete. The complete definition is elements which have partially filled d orbitals either in their atoms or in their most commonly occurring oxidation states. For this, I have got one typical example. In fact, copper with atomic number 29 has electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d10. 3d10 means it has no incompletely filled d subshell. Strictly speaking, it should not have been called a D block element, but in reality, it exhibits all the properties of D block elements, and therefore great people who have contributed a lot towards the understanding of the chemistry of some of the elements like copper, silver, and gold, they added this line also, that either in their atoms or in their most commonly occurring oxidation state. Then, to support and substantiate the second part of the definition, Copper in the atomic state has completely filled d subshell. But when you come to the case of cuprous, cuprous means copper to become cuprous, it should lose one electron. And that one electron comes from the 4s subshell, from this end. That means even in the cuprous state, it has no incompletely filled d subshell. All the d orbitals are with paired electrons only. When you compare the copper compounds in the cuprous state as well as in the cupric state, 99% of the copper compounds have got cupric ion and not the cuprous ion. Means most of the cupric compounds are stable than the cuprous compounds. So from cuprous copper, to go from cuprous state to the cupric state, it has to lose one more electron. That one electron comes from the d subshell. That means in the cupric state, it has got one electron unpaired or one orbital incompletely filled, and therefore copper is also referred to as the d block element. Same explanation holds good for silver, same explanation holds good for gold also, and therefore whenever students are asked to write the definition of d block elements, you should not end up only with the elements which are partially filled d orbitals are called d block element. You have to add the second part of the definition also, that either in their atoms or in their most commonly occurring oxidation stage. This justifies the complete definition of d block elements. Then why we should study only d block elements very specially? In what way these d block elements are distinguished from the adjoining S block and the P block elements? Because these d block elements are so special that you can see these properties which are never exhibited either by S block or by P block. D block elements show variable oxidation states. You should note that S block elements can exhibit only one type of oxidation state, whereas the D block elements exhibit variable oxidation state. These are the only elements which can form colored compounds, both in the solid state as well as in the aqueous solution. Please note, S block elements and their compounds are almost colorless. Even P block elements and their compounds are colorless, both in the solid state as well as in the solution form. These have got wonderful conducting property of both heat and electricity, act as catalyst for various reactions, form a large number of complex or coordination compounds, form interstitial or non-stoichiometric compounds, can form more malleable and ductile or sonoric in nature. They exhibit high melting point and high density. This set of properties are never seen in case of S block elements and even in P block elements. And because these offer such wonderful properties, they have got tremendous applications in different industries. Therefore, we are going to study especially these D block elements. And in this case, we have seen these d block elements are also otherwise more popularly known as transition metals. As you know, the dictionary meaning of transition is to jump from one state to another state. We know that S block elements are highly reactive. They form ionic compounds and their oxides are basic in nature. This is on one hand. On the other hand, P block elements normally form covalent compounds, and these oxides of these non-metals or oxides of P block elements are acidic in nature. But when you go from left hand side to the right hand side, in this D block, the compounds of D block elements gradually change their properties from ionic to covalent, right? That means the electropositivity decreases from left hand side to the right hand side, and contrary to this, electronegativity increases. Because of such electropositivity decrease and increase in the electronegativity, we see many wonderful properties in the subsequent slides. And in fact, the ionic character is more visible in the lower oxidation state of these D block elements, whereas covalent character is more pronounced in the elements with the higher oxidation number. In fact, Mn can form different oxides. MnO we have got, MnO2 we have got, KMnO4 we have got, and MnO is going to be more ionic, similar to these S block elements, whereas KMnO4 is more covalent, similar to such P block elements, and therefore these are generally called the transition elements because they show a kind of transition in going from left hand side to the right hand side. Transition mostly in terms of ionic character to the covalent character as the oxidation number increases from lower to higher oxidation number. Then we have three fundamental properties we have got to study, not only for D block elements, but for any element that you study in the periodic table. And one such property is called ionization energy or ionization potential. You have been taught in lower classes also the minimum energy required to remove an electron from outermost shell from an isolated gaseous atom in its ground state is called ionization energy. And in fact, in any group, ionization energy decreases from top to bottom, whereas as one moves from left to right, the ionization energy keeps on increasing. This is going to be quite interesting. This trend is going to be quite interesting in D block elements, which we are going to study in the forthcoming slides. Then we have got another property of any element just opposite to the electropositivity. This is called electronegativity. What is this electronegativity? Is a chemical property that describes the tendency of an atom or functional group to attract electrons or electron density. In a simple way, if I have to say that from sodium to chlorine, electronegativity increases means chlorine has got greater capacity to attract electron towards itself, whereas sodium has got least capacity to attract electron or most capacity to lose electron. The capacity of an element to lose the electron, as you know, is called electropositivity, whereas capacity to attract an electron itself is called electronegativity. And in any period, electronegativity keeps on increasing from left to right. This I said exactly opposite to electropositivity. Electropositivity decreased from left to right, whereas electronegativity increased from left to right. And one more very important property that one should focus on is atomic radii. It is almost similar to the radius of any circle. What is radius of any circle? The distance between the center of the circle to any point on the circumference is called the radius. Similar to that, we have got atomic radius that this is the rough distance between the center of an atom to the point where maximum electron density is experienced. And you see this trend in going from left to right, the atomic size keeps on decreasing, whereas in going from top to bottom in any group, the atomic size or atomic radius keeps on increasing. This I am highlighting at the beginning itself because these properties like ionization energy, electronegativity, and atomic radii will describe a set of special properties associated with the D block elements, and that we are going to study one after the other with this as the guide for us. How to write the electronic configuration? Please recall, I showed the classification of elements as S, P, D, and F. In case of the transitional elements. I mentioned as atomic number increases from left to right there, here from scandium to this zinc 30, as the atomic number increases, the added electron, instead of entering into the outer subshell, outer S subshell, it is entering the inner D subshell. In fact, scandium 21, we have got 3D1, 4s2 remains constant. Titanium, we have got 3D2, the 22nd electron enters the 3D subshell. Vanadium, we have got D3. Chromium should have been D4 and 4s2. Theoretically, it should have got the electronic configuration of 3D4, 4s2, but it prefers the observed electronic configuration of 3D5, 4s1. It is only because chromium wants to attain extra stability due to half-filled orbitals. 4s is half-filled as well as 3d is half-filled, and therefore there is shift of an electron from 4s level to 3d, so that 3d4 becomes 3d5 and 4s2 becomes 4s1. Similarly, manganese 25th electron enters into the d subshell. Likewise, up to nickel. When you look at the electronic configuration from scandium to nickel, the second digit of the atomic number is the number of electrons present in the d subshell. Second digit is 1, here it is 1. Second digit is 2, here it is 2, and so on, right? And similar to chromium, copper with atomic number 29 should have got the electronic configuration of 3d9 4s2. But once again, copper is little over greedy. It wants to attain extra stability due to completely filled orbitals, similar to this chromium, which is extra stability attained due to half-filled orbitals. Here it is completely filled orbitals, and hence there is a shift of an electron from 4s2 to 3d9, so that 3d9 becomes 3d10 and 4s2 is reduced to 4s1. And in this case, zinc 30 completely filled orbitals 3d10 and 4s2. That means this does not have partially filled d subshell, and therefore it should not have been called the d block element or transition elements. But if you can recall, the elements such as zinc, cadmium, and mercury are also placed exactly sandwiched between S and P block elements, because though zinc, cadmium, and mercury do not have the partially filled D subshell, they exhibit most of the properties exhibited by remaining D block elements, and therefore these are also placed in the same middle portion of the periodic table, now popularly known as D block. And that is the reason why these three metals such as zinc, cadmium, and mercury placed in D block elements are popularly known as pseudo transition elements. These are not true transition elements. Rest all are true transition elements, but these are popularly known as the pseudo transition elements. Many times in the examination, such questions will be asked. Why are zinc, cadmium, and mercury are popularly known as pseudo transition elements? Answer is very simple. They don't have partially filled d subshell, but exhibit most of the properties exhibited by rest of the d block elements. And now comes very important property of D block elements, which is never seen in case of S and P block elements. S and P block elements exhibit only one type of valency. They never exhibit more than one type of valency. But when you come to the case of the first series, second series, and third series of transition elements, where in the first series we have got scandium, the elements going from scandium to yttrium, oxidation number goes from +2, +3, +4, and so on. Manganese with atomic number 25 can exhibit all these oxidation numbers. It exhibits +2, it exhibits +4, it exhibits +6, and also exhibits +7. What is true for first series or 3D series of transition elements is also true for second series as well as third series. And as the oxidation number is varying from +2 to +7, their property keeps on changing from ionic to covalent. Their property jump from the ionic character to the covalent character, and we have got one very simple experiment in the forthcoming slide as to why and how manganese compounds exhibit variable oxidation number. And it is this variable oxidation number that becomes a guiding principle for the D block elements to act as catalyst to form millions and millions of inorganic complex compounds to make the D block elements act as wonderful catalysts and so on. That we are going to study step by step. And here you see how atomic radii varies in case of D block elements. Earlier, we saw in the rest of the periods, as one moved from left to right, ionization energy decreased, electronegativity decreased, atomic radii was increasing. But when you see in case of, especially in case of transition elements, the atomic radius first decreases, remains almost constant, and then again it increases. That means we are able to see all the three trends, right? Initially, first decrease in the size, in the middle, practically remaining constant, and in the end, almost in the end, there is increase. The reason for first decrease, then remaining constant, and then again sharp increase towards the end of the series are attributed to all these factors such as atomic radii of 3D series transition elements in general decrease with increasing atomic number. In the beginning decrease, then remains constant, and again increase towards the end. And all these is because of the very characteristic feature that say after chromium, increased nuclear charge is counterbalanced by the increased shielding effect. You must have been taught at lower classes what is shielding effect or screening effect. Then you know the net charge present in the nucleus is called the nuclear charge and so on. In one case, that in the middle, the nuclear charge is exactly neutralized by the shielding effect. And here one dominates over the other. That means we have got increase in the beginning and decrease in the end. So these two factors dominate one over the other in the beginning and at the end, but exactly neutralized in the middle, and therefore all the three trends of decrease, remaining constant, and increase is seen only in case of D block elements, never in case of S and P block elements. That should be noted down. And another unique property that we have seen in the earlier case, that D block elements exhibit unique property such as imparting color. Not only elements, but their compounds. Compounds both in the solid state as well as in their aqueous solution. Now, what is this color? For a science student, color should not be a color, it should be a wavelength. This I shall repeat, a science student should not call color as color, that should be attributed to wavelength. I have got some compounds here in the textbook, in the test tube. We have got copper sulfate, normally blue in color. It should be more strictly called cupric sulfate because copper in its +2 oxidation state is more dominating, and therefore we have got blue color. Then we have got nickel chloride, we have got potassium dichromate, we have got cobalt sulfate, we have got the permanganate ion. And when do you expect a substance to be colored? For that, one should have got the basic information of what is called electromagnetic radiation spectrum. You know what is electromagnetic radiation spectrum? The spectrum of variety of wavelength ranging from red wave waves up to gamma radiation. In this electromagnetic radiation spectrum, we have got a very, very small patchwork, right, of wavelength ranging from 4,000 angstrom minute to 7,500 angstrom minute, and this range is called the visible range, visible region of the entire electromagnetic radiation spectrum. Then the question now arises, when a substance appears colored. A substance appears colored only when it absorbs a particular wavelength only from the visible region of the entire electromagnetic radiation spectrum and not from UV region and not from any other region, right? And when do we expect that substance should be orange in color? When do we expect that a substance should be blue in color? For that, we have got little more detailed explanation, and that explanation you will see in this slide, right? We have got a substance is colored, the compounds of d block elements are colored because of the partially filled d orbitals. Whenever an element comes in the vicinity of, say, water molecules or some other negative ions, a degenerate set of 5 orbitals. You know, these 5 orbitals are dxy, dyz, dzx, dx square minus y square, and dz square, right? We have got these degenerate set means 5 orbitals of the same energy will be referred to as degenerate set. But when such a degenerate set of 5 orbitals is approached by water molecules or any ligand or by any negatively charged ion, then please note how the electron makes transition from relatively lower energy to the higher energy. Please see this transition, right? You see, I hope you are able to see the transition from lower d subshell to the higher d subshell. For this transition to take place of electron from lower energy level to the higher energy level, very little energy is required. And this little energy required for dd transition means transition from one d subshell to, one d orbital to the other d orbital. Very little energy required comes from absorption of a particular wavelength from visible region of the entire electromagnetic radiation spectrum. And if for this DD transition, blue wavelength is absorbed, its complementary color is imparted to the substance. If orange color wavelength is absorbed, then blue color is imparted to the substance. And such a splitting of the degenerate set of D subshell, right, in the vicinity of water molecules or negatively charged ions or ligands splitting into two sets, lower energy and higher energy. You must have been taught that it is popularly known as crystal field theory or CFT. And now the color imparted by a substance can be beautifully explained by this color wheel. Say color imparted. Color, as I mentioned, for a science student should be wavelength and should not call it color only, right? Color exhibited by a substance is complementary of the color absorbed from the visible region of electromagnetic radiation spectrum. Strictly speaking, when copper cube in its cupric state approaches the sulfate negative radical, right? It absorbs the wavelength from this orange range of the electromagnetic of the visible region of the electromagnetic radiation spectrum, and the complementary color of this orange is blue. That means sulfate radical makes the split in d subshell, and there is going to be an electron transition from one lower energy level to the higher energy level. This requires very little amount of energy, and that comes from orange wavelength, and the complementary color of the orange is supposed to be blue color. That's how most of the cupric compounds are blue in color. Most of the dichromates are orange in color. Their absorption is going to be blue. Therefore, the color imparted corresponds to orange wavelength. The color associated with inorganic salts, you must have observed in the lab, ferrous sulfate is light green. We have got potassium ferricyanide, light yellow in color, ferrocyanide orange in color, chromate yellow in color, dichromate orange in color. Most of the inorganic salts are made out of the D block elements, whereas 100% of the colorless salts must have been the salts of S or P block elements. The imparting color, the unique property of these substances imparting color makes a student to identify the inorganic salt very easily in the lab. And we have got one small experiment for this color change uh, or the color exhibited by the compound of D block elements depends upon the oxidation number. For this, I carried out one very simple experiment where we have got vanadium pentoxide, V2O5, put into water. I stirred it for almost half an hour. It did not dissolve because vanadium in its pentavalent state exhibits more of covalent property, and the covalent compounds do not so easily dissolve in water. Even after stirring for half an hour, it did not dissolve, but it only dispersed. I added a few tin pieces and I also added little amount of hydrochloric acid. And strictly speaking, this should have been heated on a burner to show decrease in the oxidation number from +5 to +2. But to save time, and as I was very curious to see the change as early as possible, I conducted the experiment by keeping the beaker in a microwave oven. 3 hour duration was reduced to only 5 minutes. When tin pieces react with hydrochloric acid, hydrogen is evolved. Hydrogen is a typical reducing agent that reduces pentavalent vanadium, that is V plus 5 to V plus 2. But in between, we have got some color changes. Vanadium pentavalent does not directly come down to +2 state. There are some intermediate steps. We have got +4, yellow in color, +3, light green in color. And if the reduction from +5 to +3 is completed, it has got blue color, and ultimately we have got +2, totally imparting blue color. That means the color of the vanadium compound exhibited not only depends upon the inorganic negative charge, but also oxidation number. The variable oxidation number is associated with variation in the color also. This we have seen earlier, that color depends upon not only the negatively charged associated with the metal ion, but also associated with the charge. Means variable oxidation number is related to variable color. And another very simple experiment that anybody can carry out in the lab or even at home is, we have got potassium permanganate. You know the well-known color of potassium permanganate, aqueous solution, that is purple or violet in nature. This is dilute solution made alkaline with a few drops of sodium hydroxide. And I just filtered it through an ordinary filter paper, and you can see that purple color, as it percolates through the filter paper, becomes green. Why such purple colored slightly alkaline KMnO4 solution, as it filters through the filter paper, becomes green? If somebody can think over and calculate the oxidation number of Mn in KMnO4, Mn in KMnO4 exhibits +7 oxidation state, right? And that is purple in color. Yeah, all Mn compounds in their +7 state are purple in color. But as it filters through the filter paper is nothing but, or any paper is nothing but cellulose. Cellulose is a typical polysaccharide or a carbohydrate. This polysaccharide is a reducing agent. This wonderful, steady, slow and steady reducing agent reduces Mn from +7 to +6. All +6 compounds of Mn are green in color. Very rarely we see Mn compounds in +6 state in the lab with the green color. And if we keep this green color solution for some more time, it becomes yellow, and at one stage it becomes colorless. That means color is going to be dark of the compounds of D block elements in their higher oxidation state, and color becomes dimmer and dimmer, or almost colorless in their lower oxidation state. This is a wonderful experiment. Hardly it takes little amount of alkali, and if you don't have filter paper, you can even use the newspaper. And one more very important point, that color exhibited by the compounds of D block elements not only depends upon the negatively charged ion responsible for crystal field theory, but also depends upon the ligand. We have got on the left hand side green colored nickel solution. This is aqueous, means nickel salt is dissolved in water. To this, what I did was I went on adding ammonia. That means nickel surrounded by water molecules as ligands, right? Gradually, due to the addition of ammonia, these water molecules have been replaced by ammonia molecules as the ligand. And as ligand changed from water to ammonia, there is change in the color. And this becomes a wonderful guiding principle to identify the typical complex compound. If it is green, then you say nickel is surrounded by water molecules. If it is violet, then you say that water molecules acting as the ligands have been replaced by ammonia molecules. That means there are so many reasons for the compounds of D block elements to exhibit different colors. And we have got a very unique property exhibited by D block elements, that they are wonderful catalysts. You know what a catalyst means. In the lower classes you have been taught that a substance that can alter the rate of the reaction without itself undergoing any permanent chemical change, and that can be recovered at the end of the reaction, both in terms of quality as well as in terms of quantity, is called a catalyst. 99% of the catalysts used in industries are either directly the D block elements or their compounds. Catalyst is popularly known as the backbone of any industry. Then why the D block elements alone, but not S and P block elements, can act as catalysts? This is because they have got more number of the D orbitals, incompletely filled D orbitals available, then ability to exhibit variable oxidation states. Greater the number of oxidation states, greater is the number of intermediate, unstable, very important compounds, which provide an alternate path of lower activation energy for the reactants, hence increasing the rate of the reaction. Then this, I mentioned that a substance that can alter the rate of the reaction. Alteration may be both in the positive direction as well as in the negative direction. And if alteration of the rate is in the positive direction, you know that such catalysts are called positive catalysts, and those who retard, those who increase the rate of the backward reaction, they are called the negative catalysts or inhibitors. And you see that these catalysts used will provide an alternate path of lower activation energy for the reactants, hence increase in the rate of the reaction. Metals with high melting point are malleable, can be beaten to thin sheets because the catalytic property of any substance increases as the surface area of the catalyst increases. You can read law of mass action. And the unique property of D block elements is these are malleable, means a thick sheet can be beaten to very, very thin sheet, and over the entire larger surface area available, reactants can go and accumulate, and due to such accumulation, there will be increase in the concentration of the reactants. As the concentration of the reactant increases according to law of mass action, rate of the reaction should also go on increasing, and therefore malleability and ductility of the D block elements plays very important role in making them to be used as wonderful catalyst in industries. If I can repeat this, metals with high melting point are malleable, can be beaten to thin sheets, provide large surface area, increase in the rate of chemistration, and hence increase in the rate of the reaction. All these properties attributed to the elements make them wonderful catalysts. You see, this photograph I had opportunity to take in Kuwait when I visited Kuwait in 2007. All these are the compounds of D block elements. And you know that Kuwait, being one of the Gulf countries, is the source of crude oil, and that crude oil has to be refined into different fractions, and that's how we get diesel, we get petrol, we get kerosene, and so on. You know how important the crude oil nowadays due to the ongoing war, unfortunate war going on between Ukraine and Russia. Here in India, we will be forced to pay nearly 15 to 20 rupees extra per liter of petrol that we are going to buy in future. And you should know that all these compounds of D block elements are used as catalyst in converting crude oil into petrol, crude oil into aviation petrol, crude oil into diesel. And if I can show you the closer picture, you see there the catalyst made of cobalt and manganese is extensively used in refining of crude oil. We have got some catalyst made out of the iron, made out of nickel, and this I have specially permitted. As I mentioned that I am a teacher, I wanted to show such catalyst used in the refining of crude oil for the benefit of the students. They permitted. You can imagine every drop of petrol that we fill into the tank, every drop of diesel that we consume for the vehicles, that must have been by the refining of crude oil into such finished good. And for refining of crude oil, these elements and their compounds are a must to act as catalysts. Then we have got this experiment conducted. You can see there, nitric acid is one of the three mineral acids. You know that hydrochloric acid, sulfuric acid, and nitric acid are three inorganic acids, otherwise more popularly known as the mineral acids. And nitric acid is manufactured all over the world by the well-known process called Ostwald's process. And the very principle of the Ostwald's process is ammonia is first oxidized to nitric oxide. Nitric oxide is further oxidized to nitrogen dioxide. Nitrogen dioxide, when absorbed in water, not only produces nitric acid, but the nitric oxide regenerated can be recycled any number of times. Amongst all the three equations, or amongst all the three reactions, first reaction is called the key reaction. And this first reaction is oxidation of ammonia to nitric oxide. Only to accelerate the rate of the reaction, platinum, a huge sheet of platinum, thin sheet of platinum is used as catalyst. Why platinum is used as catalyst? In this simple experiment, what I did was, I took a small amount of liquor ammonia, not this liquid ammonia. I hope you know the difference between liquor ammonia and liquid ammonia. Ammonia at room temperature is a gas. Under high pressure and low temperature, when converted into liquid, this will be referred to as the liquid ammonia. Whereas liquor ammonia is ammonia gas simply dissolved into water. I had a few ml of liquid ammonia. I had a preheated platinum wire introduced into the empty portion of this conical flask. Empty portion means air is there. I did not dip it here. And whatever the preheated platinum wire was there, that remained red hot, not for hours together, but I have tested it nearly 1 day, depending upon the amount of this liquid ammonia. Even for days together, you can keep this preheated platinum wire in its red hot condition. Why this is? Because the reaction between liquid ammonia and the oxygen of the air filled in air not only converts ammonia into nitric oxide, but along with that 900 kilojoules of energy is released. And this 900 kilojoules of energy released keeps the preheated platinum wire in its red hot condition. Probably this small experiment must have been the principle behind the historically well-known Oswald's process for the production of nitric acid all over the world. Please note, platinum is one of the D block elements. Directly metal is used. There need not be use of any compound. Likewise, we have got iron used in the production of ammonia by Haber's process. We have got iron used in the hydrogenation of oils. We have got nickel used in the hydrogenation of oils. There are variety of catalysts used in the production of different compounds, industrially different compounds, and such property of elements acting as catalyst is attributed only to those which come from the middle portion of the periodic table, not from S block, not from P block of the periodic table. Then another very important property of the D block elements or transition elements is that they are paramagnetic in nature. What is meant by this paramagnetism, diamagnetism, and ferromagnetism? In simple, the magnetic property of a substance due to the presence of unpaired electrons is called paramagnetism, and such substances, when kept under the influence of external magnetic field, right, these get attracted. Whereas the magnetic property of any substance due to the paired electrons, due to the paired electrons is called diamagnetism, and such a substance when kept under the influence of external magnetic field, instead of getting attracted, the substance gets repelled. But there is a special class of metals such as iron, cobalt, and nickel. These metals are popularly known as ferromagnetic because when such metals or their alloys are rubbed with another magnet only in one direction, the magnetic property of that magnet will be induced into such metals. That means these can be easily and permanently magnetized when rubbed with another magnet in only one direction. And all this is because D block elements, why are they paramagnetic in nature? Because they have got unpaired electrons present in the D section, right? And in few cases, there may be diamagnetic property exhibited. The elements which have got the completely filled orbitals, completely filled d orbitals may be diamagnetic in nature, but majority of them are paramagnetic in nature. And paramagnetism is normally measured in terms of magnetic momentum expressed in terms of Bohr magneton, and the paramagnetism magnetic momentum mu s is generally represented and calculated by the simple formula root of n into n plus 2, where n as usual represents the principal quantum number. You should know that most of the d block elements, due to the presence of unpaired electrons in their d subshell, exhibit paramagnetism. Not only this, even some of the complex compounds which have got at least one unpaired electron in their d subshell exhibit paramagnetism. Now, the last phase of this presentation is what are salts, how salts are classified as simple salts, double salts, and the complex salts, or otherwise more popularly known as coordination compounds or Werner's compounds. And for all this, a simple salt, you must, second PhD students must be analyzing a simple salt in the lab, where a salt when dissolved in water or any other suitable solvent produces only one type of cation and only one type of anion, should be called a simple salt. There should not be more than one type of positive radical, not more than one type of negative radical. You have got wonderful examples of sodium chloride, right? When sodium chloride is dissolved in water, you may get only Na plus Cl minus. When aluminum sulfate is dissolved in water, we get aluminum tripositive ions and sulfate dinegative ions. Maybe aluminum ions is more than one, but type is going to be only one. Then what is meant by double salt? When two simple salts unite in an equimolar ratio, this is very important. A double salt is formed by the union of two simple salts in an equimolar ratio. When dissolved in a suitable solvent, ionize completely in such a way that all the individual ions retain their inherent properties, retain their original properties. We have got some typical examples of these double salts. Carnallite, naturally available. Double chloride of potassium and magnesium. We have got potash alum, or otherwise known as alum. It is K2SO4, Al2SO4, 24H2O. 1 mole of potassium sulfate, 1 mole of aluminum sulfate. When dissolved in water, and if excess water is evaporated by heating, you will get beautiful colorless crystals which are hydrated in nature with 24H2O. When potash alum is dissolved in water, you get K plus ion, you get sulfate ion, you get aluminum tripositive ion, and again you get sulfate ion. You can easily test the presence of K plus sulfate and aluminum the way that you have been analyzing simple salts in the lab. K plus can be tested with picric acid. Then sulfate ion can be tested with barium chloride. Aluminum tripositive ion can be tested with, say, sodium hydroxide. To such an aqueous solution, when sodium hydroxide is added, first you get white gelatinous precipitate of aluminum hydroxide. If you continue to add excess of sodium hydroxide, white gelatinous precipitate formed in the beginning simply dissolves, getting a clear solution of what is called sodium aluminate. None of the ion would have lost its inherent property even after one simple salt has united with another in an equimolar ratio. Same can be repeated even with more salt. More salt you must be using in what is called ground ring test. It is the double salt made out of one simple salt such as ammonium sulfate, another simple salt as ferrous sulfate. All the ions produced, ammonium ion, sulfate ion, again ferrous ion, retain their individual identity even after the double salt formation. The difference between double salt and now complex salt is both of them are formed with the union of two simple salts. In this case, double salt, there is a condition equimolar ratio of each simple salt. But in case of complex salt, or otherwise known as Werner's compounds, two simple salts can be united in any definite ratio. When dissolved in water or any suitable solvent, the compound will so ionize, I shall repeat, the compound will so ionize that at least one ion would have lost its original identity. Best example is this K4FeCN6. This is formed by two simple salts, deadly poisonous potassium cyanide KCl and another less poisonous ferrous cyanide. When such a salt is dissolved in water, you can get positive test only for K plus ions, but not for ferrous ion, not for cyanide ion, right? And if somebody consumes potassium cyanide, he or she will be no more within seconds, but not to be tested. But still, I'm telling you, if somebody can consume potassium ferrocyanide, he or she is not going to die because cyanide is enclosed in the complex sphere. It has lost its original toxic character. It has lost its inherent poisonous character. Therefore, potassium ferrocyanide, potassium ferricyanide, cuproammonium sulfate, all these are popularly known as complex salts, right? There is no much difference between double salt and complex salt. Double salts are formed by the two simple salts in an equimolar ratio. Here in case of complex compounds, they can unite in any definite ratio, but after dissolution, at least one ion would lose its inherent property. And the credit of introducing such complex compounds or coordination compounds should go to the great Werner, who was the first Nobel laureate in inorganic chemistry. And this property of d block elements forming the complex compound should go to the central metal ion exhibiting variable oxidation state, such as ferrous, here it is +2, ferric, here it is +3. And why only D block elements can form complex compounds? Why not S and P block elements? Is because the D block elements have got small size. Though small in size, they have got high nuclear charge. Not only high nuclear charge, there is availability of many vacant d orbitals of right type of energy. That is very important to accommodate lone pair of electrons donated by the ligands. In the previous slide, please recall, we had cyanide. Each cyanide is a ligand. What is the ligand? An atom or ion or a group that has capacity to donate a pair or pairs of electrons are all called ligands. The wonderful complex compounds in our body is hemoglobin. The central metal ion is iron. It is surrounded by different ligands. And you know that red color of the blood is because of hemoglobin. It is a complex compound. Sometimes, unfortunately, in few unfortunate patients, RBC, right, count will be less and WBC count will be unimaginably in terms of several lakhs. And if WBC counts goes up and up, alarmingly up and up, and RBC count goes down and down, then that patient will suffer from blood cancer. For such blood cancer patients, almost every alternate day, there should be another complex given, and this complex given is of platinum, which is D block element, and that is called cisplatin. You will be surprised that each capsule of 250 mg cost nearly 9,000 rupees. Not made in our country. These are all imported from some other countries. But though government of India imports it by paying more, as this is life-saving drug, it is made available to the cancer patients at very low and subsidized rates. You can imagine God made complex compound where central metal iron is from D block of the periodic table, man-made complex compound, which is anti-cancer drug, where platinum is used extensively, and that also is from the D block of the periodic table, and therefore we should be grateful for several unique properties of the D block elements like acting as catalyst. They play a very important role in the formation of complex compounds and so on. Why earlier we saw that the D block elements and their some of the compounds are paramagnetic in nature because this is the electron which acts as a micromagnet. Because every electron acts as a micromagnet, the compounds are paramagnetic in nature. And you know that electron, while revolving around the nucleus, it also revolves about its own axis, and there are only two possibilities. One may be in the anti-clockwise direction and another in the clockwise direction. And based on that, you must have been taught that the quantum number, spin quantum number associated with electron is either plus half or minus half. And this plays very important role in several medical investigations, right? And magnetic momentum, I said, expressed in terms of 4 magnetons, can be measured in terms of very expensive, very sophisticated balance, not the balance that we use in the chemistry lab. This balance is called Guy balance. If one unpaired electron is there, right, under the influence of external magnetic field, what is its magnetic momentum? As the magnetic momentum value increases, it indicates that number of unpaired electrons present in the substance is more and more. This Guy balance is not ordinarily available in any college or university, may be available in research institutes like IISc. And this is the last slide before I conclude. Since I feel I am addressing large number of students and teachers as well as the science lovers, I normally end up my presentation with this great picture of Shahnai Chakravarti, Bharat Ratna, Bismillah Khan. I had opportunity of listening to him. More than listening to him, this is very rare picture of the Shahnai Chakravarti rehearsing in a thatched hut. You can see the background here, right? This I could click in 1993. I had an opportunity of listening to him, but since I had camera, I wanted to capture his very special photograph. He was rehearsing in a hut just behind the main Pendal. I just followed the music and saw this great man rehearsing. Immediately, I took out my camera. I could take his permission, click the picture, and I could also touch his feet for his blessings. And I was literally slightly emotional. Such a great man, Shahnai Chakravarti, still rehearsing at the then age of 76 before performing onto the platform. What is it we are doing this as teachers? What is it we are doing as students? Are we practicing? Are we rehearsing before we go to the platform? Before we go to the examination hall? And when the question was put to me, I only went on answering that we should also rehearse. We should also practice because it is constant practice that converts an ordinary student into an extraordinary student. And you see there 5 P's, like we have got to perceive, we have got to plan, we have got to prepare, we have got to practice and then present. Anything that you want to do, first perceive it, imagine it mentally, just see what exactly you want to do, then plan properly. What you have planned, you prepare well. Once you prepare, don't present it to the audience directly. Practice several times, like this great man practices. And then once you get confidence, then present. Don't be overconfident, right? Overconfidence is the first step for our failure, right? So this formula of 5 P's is the secret of anybody's success. I think I must have tried my best to reach out to all the colleagues who have been associated with this presentation conducted by KSTA. Once again, I just thank all the authorities of Karnataka Science and Technology Academy for having invited me, for having given me an opportunity to share my knowledge with a variety of audience, those who have joined. Thank you all.
Thank you very much, sir. You had a great presentation. Now I request participants to mention the questions if they have any in the chat box, or they can raise their virtual hand so that we can unmute them and they can speak directly to Professor and clear your queries or doubts. Before that, I request our honorable member, Professor Basuraj Moulimani sir, to say a few words on the session. Please, sir. Moulimani sir, I request you to say a few words, sir. Or if you have any queries, you can discuss, sir. I think there is some technical issue. Sir, as of now, there are no questions from the students or audience.
Yes, sir, they can even mail. They can even mail later.
They can even mail, and they can ask through call or send us mail their queries, and we can send you the questions in turn and reply to them, sir.
Yes, sir, I shall be very happy to respond.
Sure, sir. Thank you very much, sir. On behalf of KSTA and on behalf of all the participants, I once again wholeheartedly thank you for delivering this session on periodic table and metals and its characteristics for 1.5 hours. Patiently, the students are also, along with students, few of the teachers also joined, sir, for this session.
Sir, sorry, I must have taken more time.
No, sir.
Only 1 hour.
Indeed, the session was very great going, sir.
Yes, sir. Thank you, sir. Very kind of you. It makes me responsible.
Thank you very much, sir.
Yes, sir. Yes, sir. Thank you very much, sir. Thank you.
Also,
thank you.
now we can conclude the session with vote of thanks formally.
Yes, sir.
First and foremost, I would like to thank once again Dr. Keshav Bulbule sir for the session. And also, I would like to thank our chairman, Professor S. Ayappan sir, Professor and CEO, Dr. M. Ramesh sir, and all my senior scientific officers, Dr. Anand sir and V.K. Srinivasu, and most importantly, our honorable members of the KSTA, Professor B.G. Moulimani sir, Professor S.K. Saidapur sir, Dr. H.A. Rangnath sir, Dr. H.S. Savitri ma'am, Professor Katre madam, and Dr. Raja Saab sir, and Dr. Bulbule Reddy sir, who have been guiding us along. And also, I would like to mention Professor V.G. Talwar sir, who have been guiding us for conducting such technical sessions and many science and technology outreaching programs. On behalf of all the students and on behalf of KSTA, I once again thank you all these members and resource persons. Last but not least, I would like to thank all the participants who have joined this session, both in WebEx platform and in YouTube channel. Thank you very much. Soon we will be hosting other sessions also. Please stay tuned with our social media and website so that you will get the upcoming programs details also. Thank you very much. With this, I end this session. Thank you very much. Have a great time once again. Thank you, sir.
Thank you, sir. Thank you.